Okay, now we will discuss the sinking of supports, how the sinking of supports influence the final end moments in the frames and also in the beams. If as I told you, if you have a statically determinate structures, either you have take a cantilever beam or simply supported beam, okay, or double overhanging beams. If any one support sinks down, no additional reactions, no moments, nothing will develop because of the sinking of supports. Because in a statically determinate structure, just a sufficient number of reactions are available to keep the structure in equilibrium and in stable condition. No additional reactions are there. So because of that, any support reaction, external effects happen to the supports, let us say, then support comes down. Then as a rigid body it will rotate, or as a rigid body it will translate. No reactions will develop in the structure. If you have a statically indeterminate structure means what? We have more number of constraints than the number of equations of equilibrium. So if at all any support sinks or yields or temperature effect, anything will produce some reactions in some part of the structure or in entire structure depending on the configuration of the structure. That's what I told you in the statically indeterminate truss analysis. Now similar to that we will take now in the frames, either it is a beam or frame, how sinking of supports influence the reactions. Okay, so we'll see now portal frames with sway. Portal frames with sway, MDM, moment distribution method. Now portal means entrance. Portal frame means frame at the entrance of a structure. Portal frames means frames provided at the entrances of structures. Supposing that for this room, that is entrance, at that entrance whatever frame you provide, that we call it as portal frame. For this entire building outside there is one entrance, and there if at all you provide a frame, that becomes portal frame for the entire building, like that. So portal frame, now we say that portal bracing, suppose in steel structures, again we'll discuss that. That means bracing provided at the portal of a bridge structure, we call it as a portal bracing. Okay, so like that, portals means entrances of the structures. Now we want to discuss portal frames with sway. If at all portal frames, earlier I gave you one example where one frame it didn't sway because of the horizontal reaction provided at the beam level. Now if at all the frames sway, how it influences the final end moments. For that, first we will discuss how the sinking of supports will influence the moment reactions. First concept, sinking of supports. Why supports sink? Assume that we have a frame like this. This, let us say A, B, C, D. Here at C and D, what is there? The fixed support means what is that actually exists is footing. Here there is a footing, here also there is a footing. And this column is embedded into the footing, and footing rests on the soil. Now assume that here there is a hard soil. Means the strength of the soil is more, so that it will not sink. So soil is so strong that footing will not go down. Here let us assume that some soft soil or say weak soil is there, or some clayey soil, let us assume. Because of that clayey soils, what happens? Supposing that water level increases or liquefaction of the soil happens, let us say, then so the support will simply sink. So when it is sinking down, supposing that it will sink, say up to here, D has come to D dash, let us say, it has sunk down by an amount of delta. When this support is sinking down, not because of the applied loads on the structure, but because of the soil problem. Assume that it moved by delta. The cause of that delta is not because of the load, some other external influence, which is not in the control of the frame. Okay. So if it sinks down, with this column also will sink down, with that beam also will come down, then it will take some position B dash, say something like this, it will come. This is called differential settlement. In soil mechanics, we have studied about that differential settlements. Okay. So B will come to B dash. This value is also now delta. Why B has come down to B dash? The beam failure does not know. It simply went down because it is connected to column. Column went down. Why column is going down? Beam doesn't know. So it simply moves with that. Now to maintain, because A and B are rigid joints, to maintain that 90-degree angle. Rigid joints means what? Angle before application of the load, angle after application of the loads, angle must remain same. In an attempt to make 90-degree angle as it is, the moments will develop at the rigid joint. So high those moments are that if you don't take proper care about those additional moments, the joints will crack. That's why if at all your concrete structures are there, let us say, one of the footing sinks down. When column also sinks down, the wall will be so heavily stressed that you will see the cracks in the walls. That is because of the sinking of the support. Okay, first at the joints also, beam and column wherever it is jointed, if big beam comes down and at the corner also cracks will develop because you didn't take care of that external the moments 6EI delta by L square. How that 6EI delta by L square comes, we'll again prove that. So that 6EI delta by L square amount of moment will develop. If you don't take care of that moment, it will, the proper reinforcement is not done, then they will break. So we must now know how the sinking of supports will produce the moments. Now, time being, let us assume that they are very strong. Columns are so strong that 90-degree angle is maintained as it is. But their 90-degree angles will not be there. Means rigid joints are there, say 90-degree, the 90-degree angle will be maintained and it will not rotate also because columns are so strong. But generally columns are not so much strong. So joint B rotates, but 90-degree angle will be maintained between the two members. Now time being, assume that columns are so strong that the the rotation didn't happen. Okay. Now cut the beam here, plug the beam out, keep the beam here. Now we are interested only in the beam A, B. This fixity is because of the columns. Columns are so strong that those columns are not permitting the beam to rotate at the joints. So that rigid joints, strong joints, we are idealizing them like this. Fixed support means there must be something. It can be a wall, it can be a column, heavy column, so that joints will not rotate. So the mathematical idealization of this problem is this. Now B comes down, say, the deflection profile, because slopes have to be 0, it will go like this. Okay. Now this is delta. Now to make the 90-degree angle to happen here and here, the fixed end moment will develop like this. This amount is 6 EI delta by L square. How to get it? We will again see that. This is also 6 EI delta by L square. Why both are anti-clockwise moments? See, no load is there. Still moment developed because of the sinking of support. Okay, when the support sinks down, that support will pull the beam down with some action. Okay, Now we'll see that why both of them are anti-clockwise developed. To determine the direction of the moments, this is what we have to do. To determine the direction of fixed end moments. What we do is, we first will permit the slopes to happen like this. You take a simply supported beam and assume that it has one of the supports sinks down by an amount, say delta. B comes to say B dash. This is say delta. Now here the slope is theta. This is also theta. To determine this direction of theta, what we have to do is, this the black color is initial position, blue color is final position. So from black color to blue color, first to get that, first to translate up to B dash. Now to get the blue color line, I have to rotate clockwise. Okay. So this is the deflection profile if at all the fixity is not there. Now the purpose of the fixed support is to make the slopes 0. I told you earlier also, fixed support always, the fixed end moment will develop. Its sole purpose is to make the slope 0. Now we'll fix it here. What its business is to make the slope 0. If at all this support will exert on the beam a clockwise movement, say, then theta will increase. But purpose is not that, it should make the slope 0. So this fellow should go here and push him up like this. Then theta becomes 0. Like this. So this is anti-clockwise movement. That's what we have shown here, anti-clockwise movement. Come to this one, you fix it. What this support should do here, if this is anti-clockwise movement, if you think that it should, if this is anti-clockwise, it has to be clockwise. If you think, say, to balance this one, if you put clockwise, again theta will increase. Purpose is not to increase theta. Purpose is to make the slope 0. To make the slope 0, this support must go here and press him down. Otherwise, if you apply like this, theta will increase more. So it will apply a moment like this. Then what will happen? You see, in the process, both of them are anti-clockwise. Now the deflection profile will be, see, it is going up. Like this it will deflect. So there is one point of inflection always due to the sinking of support. You see here, profile is like this, means this is hogging, this is sagging. So there must be one point of inflection. So that's how the diagrams have come. Now coming to this one. Now that you have understood these two directions are correctly drawn, MFAB, MFBA are fixed end moments. Now you see, this is 6A delta by L square, this is 6A delta by L square. Total moment is 12A delta by L square. Now we have to see the equilibrium part. First make the slopes 0, fix the directions. Now it should be in equilibrium. Then this moment 12A delta by L square, who will balance? These two supports will offer forces, like a couple it will offer like this. This formula we know, this VA is M by L. Total M is 12 VI delta by L square divided by L. So you will get 12 EI delta by L cube here. This also 12 EI delta by L cube. Okay. Now this structure is completely in equilibrium. Now this red color force, who will give? This force is exerted by the support on the beam. Otherwise, why it will go down? Because it is statically indeterminate structure, that sinking causes some forces, and whatever direction delta happens, in the same direction pull also must be there. Your Castigliano's theorem 1 tells you that only. In a structure, if you have, say, delta displacement happened, then force developed will be in the same direction. If you want to find this Vb, then first derivative of energy with respect to displacement, you will get force in the uh, uh, force or resistance developed by the structure in the direction of the displacement only. That's what Castigliano's theorem 1. And to get or to use Castigliano's theorem 1, we must write the energy in terms of the displacements. Then differentiate that energy with respect to displacement. You will get force to be applied in the structure in the same direction of the displacement. So that's how it comes. Now we visualize this one like this. You assume that B has come to B dash. Why unnecessarily it will come to B dash? Someone might have pulled him. So hold him, pull him down. This is the action 12 delta by L cube. Because of this force, this much delta happened. That means this force to be applied is a function of the displacement. Okay. So now this is the action. Due to this, all the reactions will develop. So this we can take say action. And this now in the form of a reaction, it will develop like this. This is a reaction. To make sigma y 0, this is also reaction. To make the slopes 0, this reaction must develop. So this much reaction will develop because of this action. That's what you have to, if we should visualize. Assume that the joint B is pulled down by a force of 12A delta by L cube, then displacement delta happened, and so all the reactions will develop to keep the structure in equilibrium. So this is how we must visualize. Okay. So your conclusion now is like this. Here also, because it is a statically indeterminate structure, this sinking produced so many forces. Okay. If at all both ends are simple supports like this, then there will not be any additional no reactions at all will develop freely. As a rigid body, it will rotate. So, conclusion. Imagine that joint B is pulled down. I think this point will write here. This conclusion will write here. Imagine that joint B is pulled down by delta due to the action of VB is equal to 12 EI delta by L cube. Then fixed end moments 6 EI delta by L square are developed at the supports to make the slopes 0. To make the slopes 0. So this is our understanding of the first concept. Supposing that instead of both ends having fixed, one end is fixed as is, one end is hinge support, let us say, then how the fixed end moments are developed? That we see in the second point. Now we should know that how that 6A delta by L square comes, we will derive it at the end of the concepts. Now, second concept is this one. Assume that this is a fixed support. It is not necessary that both ends will have to be always fixed supports only. It can be hinge support also. Now, support B sinks down. Why it sinks down? Again, not due to the applied load on the structure, but due to the soil problem, let us say. And that support is pulling the structure down. If the column, here column is there, say, column will pull the beam down, otherwise beam will not go down. Then how much force it should pull so that the delta will happen? This is delta, let us say. This is the deflection profile, because slope has here moment has to be 0. Now to make the slope 0, here fixed end moment will develop. It is also statically indeterminate structure. Propped cantilevers are statically indeterminate structures. So sinking of supports will produce some reactions or moments. Now we want to know how much reaction is developed here or here, how much force is required, or how much force should the support exert on the beam so that it can go down or it can pull the beam down. We want to know. Suppose this profile we don't know how to manage, say. To get that result, what we do is, known problem we'll take it, because we make use of the moment distribution concepts. What we do is, first you fix it. Why should we fix it? When you fix it only, we know the formulas. So this is A, B, let us say. This length is L. Fix it, sink it by delta. For that case, we know how much moments are developed. This is delta. This we know, 6ci delta by L square. Here, this is 6ci delta by L square. Now, this is what you are actually at the support B, there is a hinge support, but we don't know when hinge support is there how to manage. So unnecessarily you fix it. You fixed it, pull it down. Now release it. Once you fix it and release, this is anti-clockwise movement. Unnecessarily you fixed it. Now you apply clockwise movement. This is actually not a fixed support. It is a symbolic representation of fixing the support and pulling him down. Simply symbolic representation, that's all. Okay, fix, pull, release. Release the fixity. Then this is anti-clockwise. Now apply clockwise movement. This is how much you have to apply, 6a delta by L square. This, since you unnecessarily fixed it, this movement is called, I told you earlier in MDM, release. So this is called release. Who should release? We only have to release. So we went and applied a moment of 6a delta by L square. If you apply 6a delta by L square, how much of moment is carried over here? Half of that is carried over. So it is carried over of 3ei delta by L square. This moment we call it as carryover moment. Now you see what's the net moment here? 0. Tallies here. Now net moment must tally here. 6 anti-clockwise, 3 clockwise. So net moment here is, this you will get anti-clockwise 3 ei delta by L square. How to get it? This is from the principle of superposition. That means the principle of superposition you can apply for the problems involving temperature changes, sinking of supports, yielding of supports, and the fabrication errors. Generally, the sinking of supports will not be so big. If sinking is so much high that if the material of the structure is loaded beyond proportionality limit, then principle of superposition may not be applicable. But we assume that all the structures in structural analysis, the displacements and yielding or sinking, etc., are small, that the principle of superposition are still valid. Linear elastic structures. Large deformations, anyhow, we don't discuss. For small deformations only, our deflections theory also applicable. So for such cases, we can write like this, 3a delta by L square. So if they ask you principle of superposition is applicable to sinking of supports means applicable to sinking of supports, because we have applied here strength of materials, temperature stresses we have applied, then sinking yielding of supports, in arches we add the individual effects, fabrication errors. If one member is too long or too short in the trusses, there also we took the principle of superposition to get the net forces. So when the loads are within the proportionality limit, we can apply or we can use the principle of superposition to get the net effect. So here you will get, now this value is 3 EI delta by L square. Now here naturally net moment is 0 because the hinge support. Now you see how to keep it in equilibrium. Anti-clockwise movement, to balance it, a clockwise couple should form like this. This is VB, this is VA. M by L, total moment is 3 EI delta by L square by L. So you will get 3 EI delta by L cube. So this also must be 3 EI delta by L cube. Now this structure is completely in equilibrium. Now why the support sinks down by delta? Because of this action. If you apply a force of 3 EI delta by L cube, a propped cantilever will sink by delta. Now this is your action. Due to this as a reaction will develop here. This also as a reaction. So these reactions will develop to keep the structure in equilibrium. We must see that way. Okay. So this much simple. You must understand how this has come. Then on this deflection profiles only, in the exam numericals also will come. Have you seen anywhere this type of deflection profile? It's like a, if you visualize this one, it's like a cantilever subjected to a point load of 3A delta by L cube, so that it went down by delta, and so that moment developed 3A delta by L cube. Same structure, fixed support, instead of hinge support, remove the hinge support, I apply point load, it becomes like a cantilever. Same deflection profile you will get. This is what we have studied in strength of materials. See here, this now first point I will remove. Okay. Now, this problem, instead of hinge support, I remove the hinge support. At the hinge support means only one reaction. This I will put it like a cantilever beam. See here, this is what I am talking. Assume that we have a cantilever beam, black color one. Now VB was there. I apply a load here. If I apply a load W, there I called VB. VB is 3I delta by L cube. Now we are applying a load W. Okay. Now the deflection profile for this structure, there blue color one, here also blue color deflection profile. See, same profile. This profile, that profile matched. Now you see, this is A, B has come to B dash. This value, let us say delta. What is the formula you have? WL cube by 3EI. This moment, how much you get? MA. We know W into L. Now there the formula is 3I delta by L cube. That value you can get from here also, you see. Delta is equal to WL cube by 3EI. So from this I can get W is equal to 3EI delta by L cube. If W is 3EI delta by L cube, what is MA? W into L, 3EI delta by L square. See, I can get MA. That means if this is the load W, when the load values we know, let us say W we know, then to find MA it is W into L. And to find the deflection, you have used Castigliano's theorem 2. There in the theorem 2, we write the complementary strain energy. Complementary strain energy means, as I told you, complementary strain energy means energy written in terms of W. Strain energy stored in terms of W, if you write it, that is called complementary energy. If you write strain energy in terms of delta, that is, we call it as simply strain energy. Okay, for linear elastic structures, complementary energy, strain energy, both of them are equal. So we write as if here also strain energy only, but true word was complementary strain or simply complementary strain energy we can use. Okay, now as per Castigliano's theorem 2, if strain energy is written in terms of W, which I told you we call it as complementary energy, complementary strain energy. So complementary strain energy, if you write in terms of W, then theorem 2 what it tells you? Strain energy, the first derivative of strain energy with respect to load at that point gives you displacement. Okay, so from theorem 2 you will get how much is delta if W is known. From Castigliano's theorem 1, what it tells you is if delta is known to you, displacement is known, say, then you will know how much force is required to push or to get that much displacement. Okay, so 3a delta by L cube you will get if you know that delta value. So it is like that only. See here, this profile, that profile, same. That means whatever moments, that 3a delta by L square must be equal to MA. MA is nothing but W into L. If you write W in terms of displacement, 3a delta by L square, both of them are identical. First thing is you are writing in terms of load. Second one, you are writing same moment in terms of the displacement. In strength of materials also in the examination, instead of giving the load, they give you some displacement delta, say WL cube by 3a value they have given. Then you can find moment like this. MA is 3a delta by L square, you will get the moment developed at A. Okay, depending on the quantities they give you, you can use W into L as the moment or 3a delta by L square as the moment. One more understanding is once deflection profiles match, then all the moments related to that, then these are identical. Simply take that value, stick it here. They will be same only. Okay, this is about the concept 2. Now let us see one more problem where both ends are hinges. That we'll see in the third concept. Now you see, you found that if both ends are fixed, to produce delta displacement you require 12a delta by L cube. Once one end is hinged, 12a delta by L cube became 3a delta by L cube. That means 4 times the force required will reduce. Next, third point concept is this one. Now both ends are hinge supports, let us say. This point, let us say A, B. See, strength of materials you have studied, one end hinge, one end roller. That is simply supported one. though they are only statically determinate structures. If you have both ends hinged like this, it is statically indeterminate structure. Now, if at all the support sinks down by delta, then the deflection profile is a straight line. See, this is a delta. Now, when compared with AB, AB dash length is more. Length is more means that means it vertically it came down. So it didn't come inward. So the blue color length of the line is slightly more. That means length increased. That means it should be under tension. No bending moment will develop. Why no bending moment in the AB member if both ends are pinned? See, AB member behaves now like a link. It is elongated by some amount, whatever little amount. Okay, this member is connected by smooth pins at the ends and not loaded at intermediate location. Such members, I told you in the trusses chapter, it behaves like a link. Link is an axially loaded member. It can, there will exist the tension or compression only. Okay. Now, so this one, there will be VB, here VA. This has to be VB only. Okay. So, this is a clockwise couple. Now, it's a couple formed. To balance that, anti-clockwise couple should develop. This is HA, HB. Now, you see, this is anti-clockwise couple. Now, the resultant of VB and HB must be in this direction only. Reaction RB, here, the resultant of this and this is like this. This is VA if I show like this. It has to be VB only. This is RA, must be equal to RB only. Like this. Okay, so it gets pulled. Deformation will take place like that. Okay, now it is completely in equilibrium. To keep two forces in equilibrium, now there are two forces only, RA, RB. To keep those two forces in equilibrium, they must be equal, oppositely directed, and collinear in action. All the things are satisfied. Now structure is in equilibrium, so it will not bend at all. If you want to find, say, HB, let us say, if delta is known to us, take moments of all forces about B dash is equal to 0. So plus VA into L minus HA into delta is equal to 0. So from this we can find HA, what is horizontal thrust developed, also we can find VA into L by delta, or whatever unknown we want we can get. So there will develop some amount of VB also in this case. So VB again is HA into delta by L, like that. So some forces will develop. It is a statically indeterminate structure. If both ends are hinge supports, it is a statically indeterminate. Whatever amount of tension develops. If at all you want to neglect this delta, say, then small amount of forces only will develop. If you want to make them as 0, RB is 0, then RA will become 0. So small forces may develop, but they will be, if you want to consider them as 0, fine. Otherwise, if they ask you exact free body diagram, that free body diagram goes like this. Okay. So next, now you see, first 12A delta by L cube, next 3A delta by L cube, then very small amount of force. If at all you have a roller here, then it is a statically determinate structure. Concept 4. Now let us see the last case. Assume that you have a roller here. Strength of materials you have learned that one end hinge, one end roller is a statically determinate structure because three reactions will develop. You have three equations of equilibrium. Now in this case, if at all the support sinks down, why it sinks down? Beam doesn't know. If at all it goes down, the rollers roll inside slightly like this. Up to here it may come. Now AB and AB dash will be equal. This is delta. This inward displacement, if you want, you can neglect. This is a second order displacement. How to get this inward displacement? Delta into theta. If at all two displacements you multiply, it is called second order displacement. Delta into again small theta will be there. So delta into theta is BB dash horizontal displacement. This little horizontal displacement. This you can neglect, but not this one. This is a first order displacement. Okay. So to that extent, once it goes down, say this goes in, that inward displacement you can neglect. Okay. So now the length will not increase. So AB dash is statically determinate structure. So VA is 0, HA 0, then VB is also 0. That means this support will not pull this fellow. Without pulling also, when the support is going down, why that column is there, let us say. When that column is going down, why it is going down? Not because of load, but because of the soil problem. And when it is going down, whatever that is resting above, that will also come with him. Freely it will go down. Then beam also will freely, rollers also will go down. And in the process, rollers roll inside, so that no stresses will develop here. So as a rigid body, it will rotate. But whereas as a rigid body, it will not rotate, AB dash, it will be pulled axially. Okay. So length increased there. So net moment anywhere, everywhere is 0 only, because it's a link behavior. So this is statically determinate structure. In this case, the values, these reactions are exactly 0. Statically determinate. That's what I have told you. Due to sinking of supports, no reactions are developed in statically determinate structures. This is what we have told. So first is 12, then became 3, then became very small, then became 0 itself. So that is how the magnitudes of the support reactions from the indeterminate structure, more indeterminate structure first case, both ends fixed means. So that way. Now here we can also write, this is first one. In this case here, it behaves like I told you that point, it is like a link. We can write that point here also. When both ends are hinge supports, beam behaves like a link. That is like an axially loaded member. This is for this case. Okay. That's why this is simply subjected to pull. That's it. So now 4 concepts we have taken. As a fifth point, what we have to know is why that 6A delta by L square moment will, how that formula comes. That we'll take up now. Okay, now we want to prove that 6a delta by L square, how it comes. This is the fixed, both ends fixed member, let us say. This is a B. One support sinks down. This is delta. So that the reactions will develop, let us say VA, MA. We want to find them. In the Macaulay's method of double integration, in strength of materials, when you have studied, loads are given, your aim was to find the deflection or slope of the deflection profile. Now displacement is given, now you want to find the force. Still we can use Macaulay's method of double integration like this. Now you take any section x6. This is what you have done in SM. At a distance of x. Okay. Now your x and y axis we can take like this. This origin. This is your x axis. This is your y axis. Because displacement happened in the downward direction, y axis I took downward. So if you take upward also, our choice as strength of materials you have studied, whatever way you have learnt. Now mx, bend moment at xx. How to find bend moment at xx? Stand there. You can now see either left side or right side. We'll see left side. Then plus VA into x because sagging moment minus MA. In Macaulay's method of double integration, if couples are acting, then you must specify where that couple is acting. Like this, MA from this section XX, this couple is at a distance of x. But if I write MA into x, it is not a moment. So I put x power 0. Then MA into x power 0 is 1. So these such functions we call them as Macaulay's functions, we take it. So we have to integrate taking that function as a Macaulay function. Now you will take EI d square y by dx square is equal to minus mx. Why should we write minus mx? If I take with respect to this coordinate x and y, as x increases, the sagging moment is there, say, curvature decreases. So as x increases, curvature in a sagging bend moment case, curvature is decreases. So curvature is minus, negative we write. Here negative sign implies that x increases, curvature decreases. If at all, sir might have told in strength of materials, if you take y-axis upward, then you will write EA d square y by dx square is equal to plus mx only. Okay, with respect to that sign conventions, that's all. Now great thing here. Now this one, if you integrate once, integrating, so minus mx means you will get minus VA into x plus MA into x power 0. When you integrate it, what you will get? EI into dy by dx is equal to minus VA into x square by 2 plus MA into x plus some constant of integration. Again integrate. That's why it is called double integration. EA into y is equal to minus VA into x cube by 6 plus MA into x square by 2 plus C1x plus C2. Okay. So this is your deflection equation. Entire profile can be described by this one. That means if there is no load, if it goes down to some point load is there, moments are there, the deflection profile is a third degree curve. Okay. Now how many unknowns are there in this equation? VA, MA, C1, C2. 4 unknowns are there in the deflection profile equation. If we, that means 4 boundary conditions are required to solve this one. What are the boundary conditions? What is the meaning of boundary conditions? Is known conditions at the ends or intermediate location, whatever it is. At A, at x is equal to 0, slope is 0, deflection is 0. At x is equal to L, if x becomes L, slope is 0, but deflection is not 0, but deflection is plus delta. So for known quantities, that means delta is known to us. So we can find the deflection profile equation. So see here, at x is equal to 0, dy by dx is equal to 0. So x0 dy by dx0 means c1 becomes 0. So from this you will get c1 is equal to 0. C1 is a constant of integration. What it tells, it gives us, or it is the C1 represents the initial slope. That means at x is equal to 0, what is the slope of the curve? That's why in the fixed supports, C1 and C2 are always 0. C1 represents initial slope. Initial slope means slope at the beginning. Initial slope of the curve. Okay. Next, second boundary condition is at x is equal to 0, x is equal to 0, y is also 0. So if you substitute here, C2 is equal to 0. That means C2 is a constant of integration, C2 represents initial deflection. When x is equal to 0, what's the deflection? C2 will tell. Next, third one. At x is equal to L, dy by dx is 0. Let us call it as equation A. Dy by dx 0 means this is 0, Va into L square by 2 plus Ma into L is equal to 0. So one equation I will get. Fourth one, at x is equal to L, y is equal to delta plus delta. This is, here C1, C2 already 0. This is delta. Ei delta is equal to minus Va into L cube by 6, Ma into L square by 2. Solving A and B. You will get Va as 12 Ei delta by L cube, and Ma you will get 6 Ei delta by L square. So from the Macaulay's method of double integration, we can get these two quantities. Macaulay's method of double integration, if displacement is known to us, you can find forces, or if the forces are known to us, then deflection profile we can draw that way. Okay. Now, if C1 and C2 are known, that means initial slope, initial deflection, if those constants of integration are known to us, we can define entire deflection curve. They are called, C1 and C2 are also called degrees of freedom. They represent independent displacements. C1 and C2 represent degrees of freedom or independent displacements. If forces are known to us, these independent displacements you can find. If that displacement is known, we can find force required to produce that much displacement. So accordingly, Castigliano's theorem 1 and 2 are also defined. Okay. So represent degrees of freedom or independent displacements. That means if you know C1 and C2, I can define the entire curve, deflection curve. Okay. Next. So now we have understood how that 6a delta by L square or 12a delta by L cube comes. Now let us see the sixth concept, where if a joint, this joint B vertically moves down, we call it as sinking. If it moves horizontally, we don't call it as sinking, we call it as sway of the structure. Sixth point, if a joint moves vertically, it is called sinking. If it moves horizontally, it is called sway. Now let us see, same members, only direction will change it, that's all. This is one member, let us say A, B. Column we have taken. Due to some reason, not because of applied load on the member, but because of external effect on the joint. So due to some wind load is acting on the joint, say, so wind load or earthquake load, whatever it is, and they are acting directly on the joint, not on the member. So it will sway joint. This is the ground floor, first floor level, it sways right side, say, like this. This we don't call it as sinking, it is called sway. Okay, 90 degrees is maintained. This is called sway. Then whenever you see this type of profile, you will get, I have given you that point earlier, 6 EI delta by L square, same horizontally earlier was there, now I turned vertical. Other than that, nothing extra we have done. This is 6 EI delta by L square. This is a reaction. This also you will get 6 EI delta by L square. This is also reaction. Then here there will develop HA 12 EI delta by L cube. This is also, you can say, reaction. All the things happened because some push was there here. Otherwise, B will not go to B dash at all in the first place. That means there is an action of this much, 12 EI delta by L cube. Due to this action, joint swayed by delta. And so all reactions developed to keep the structure in equilibrium. Okay. Now, next point. Supposing that if you have, this is a hinge support, let us say. Now this is a fixed support. Fixed means compared to the column, beam is heavy beam, let us say, infinitely stiff. Then when it sways, the deflection profile will be like this. Here slope will be 0. Fixed support means, as such, fixed support, it can be a heavy beam or it can be a wall or ceiling, whatever it is. And if such as a rigid body, if that moves, the deflection profile now will go something like this. 90-degree angle should be maintained. Then it's like a cantilever deflection profile. A cantilever beam is a cantilever beam, say, apply a point load, you push it, it will deflect like this. That and this are identical. A cantilever beam subjected to point load at free end is identical to one end fixed, one end hinge support, and one of the supports, either hinge support or fixed support, moves by delta. Both deflection profiles are identical because forces everything same. Now you see here moments, 0 moment. Here you will get 3 EI delta by L square as a reaction. Here the moment is 0 and force here is HEA 3 EI delta by L cube. This is a reaction. All the things will develop because of an action which must be applied here, HB. This is 3 EI delta by L cube. This is your action. From here to here, this is delta. Okay. So if I apply this much force, this can be due to wind load. acting on the joint only, not on the member. So that joint, if it stays there only, supposing that no forces will be there, if it moves or if that force produces delta, then other reactions will develop like this. Okay. So the sway means horizontal displacement, sink means vertical displacement. Formulas are same. Now with this understanding, now let us see the numerical questions. Find vertical deflection delta. Delta of the rigid block shown in figure. Rigid block of weight W. Now see, this is our problem. This two A, B, C, D are two beams. Its length is L, moment of inertia I. Length is L, moment of inertia I. This is a rigid block whose weight is W. Then they should also give us the deflection profile. That means rigid block means it will not bend, and displacement for small displacements, it goes say vertically down only. Then the deflection profile is something like this. This also in the same way. This profile also they will give us, so that this will behave like a like this. Okay, so that the 90-degree angle before, 90-degree angle after, and also joint will not rotate. Okay, this is like a rigid body, B has to come B dash. This rigid block means that only. So stiff it is that it will not rotate. So vertically it went down. If it goes down, assume that the blue color one is the final displacement. This is a delta. Here also it has come down like this, say. So blue color one is this AB, CD is the beam. This has come to D dash. B will come to B dash. So delta displacement. How much the rigid block has deflected down? Two beams are there kept horizontally. Both of them are supporting a block of weight W. And the block comes down because this weight has to be taken by the beams, and beams deflect. And the deflection profile also given for us like this. Whenever you see this type of deflection profile, we know how much moment, how much force is required. 12A delta by L cube. Moment developed are 6A delta by L square. Wherever you see this profile, simply 6A delta by L square, 12A delta by L cube, automatically we should write, because there is the fixed quantities there. If you know the deflection profiles, in the exam the questions will be given such that the deflection profiles are already known to us. In strength of materials also we have seen. So those profiles only will be given to us, so that within 10-15 seconds we can complete a 2 marks question. Now since we know this profile, 6A delta by L square and 12A delta by L cube. Now second point, both beams are equally strong, Li. Your W, whatever W you apply, both beams will share equally. Entire load will not act on this one, because it is going down by delta. This is also going down by delta. Because of the compatibility condition, both members have to displace by delta only. If this is delta, this is 2 delta, let us say, then that means block is broken. That much gap, where will we get? So that is called compatibility condition. Delta for AB beam, delta for CD beam must be same. So only it can go by as a single unit. So your W will be shared by the two beams equally. So out of W, this will take W by 2, this will take W by 2. That you will see from the structure. Now cut this beam. We are not interested in the entire story. We are interested only this part. Why we are interested only in this part? Because for that part only the deflection profile is known to us. So cut, pluck, keep it side. This is our problem. This fixed support, it may be a wall or a rigid block or whatever it is. Okay. This point, let us say AB. This B has come down to B dash. I can write like this. This value is delta. B has come to B dash. Why it will come down unnecessarily? Somebody must pull this support down. Otherwise, here no load is there. Why it will go down? Someone must pull the joint. With how much force? This we know. VB is equal to 12 EI delta by L cube. This value he has given W by 2. Given. So what is W? Now what is delta now? WL cube by 24 EI. In 2 minutes time, our task is only this much. Okay. Now, this is W by 2. To keep sigma y0, how much VA should be? W by 2. Otherwise, sigma y0 will not happen. Now, the fixed end moment 6 EI delta by L square. Here problem is over. This is 2 marks. Now, some complete observation we are writing. This is also 6 EI delta by L square. Now you see, what is the maximum shear force and maximum bending moment? That also we can find. Maximum shear force and maximum bending moment in any beam, or this also they can ask. So maximum shear force means how to find. I told you earlier, section XX. Shear force, if you want to find at any section in the beam, stand there, look one side. Which side? Whatever side we want, we can see. Whichever side is easier for us to manage, that side we see and get out of the problem fast. So stand left side, section left side upward positive. So maximum shear force is equal to, stand at XX and look left. Don't want? We can look right also. So you will get plus W by 2. Maximum bending moment. When load is not there, bending moment will develop at A only, because this is like a fixed end moment. 6 EI delta by L square. 6 EI delta means WL cube by 24 EI by L square. So you will get WL by 4. So W by 2, WL by 4 is one of the options. Supposing that if they ask you, how the shear force diagram and bending moment diagram look like. Supposing that will give you some more input, some more idea about the problem, how the beams behave. This point, let us say AB, it sank down by delta, so that VB you got it as W by 2, VA is also W by 2. This moment anti-clockwise MA, WL by 4, MB is also WL by 4, because moments must be same. This strength of materials, many problems we have drawn. So SFD, see here, stand here, look left, W by 2. Stand here, look left, same W by 2. If two positions you stand and look one side, you get the same result, say, then SFD is a rectangle. Section left side upward is positive shear force. This value is W by 2, W by 2. This is your shear force diagram. Then bend moment diagram. See here, to find bend moment diagram also, if end moments are known to us, bend moment at x and for different values of x, that is story we should not write. That will only waste our time. Stand here, look left, section left side anti-clockwise, it will hog negative bending moment. So push it down. Its value is WL by 4. Now stand here, look right side. Again same anti-clockwise. But section right side anti-clockwise, it will sag. But you cannot say stand here, look left side, section left side clockwise is again hogging, you cannot say. Because you cannot stand here first of all. If you stand here, you will fall down. When you are falling down, whether sagging, hogging, you cannot find. Because no beam at all to sag or hog. So you must stand on the beam. Now look one side. So this will sag. So positive bending moment like this. Now when no load is there, we have known that bending moment diagram must be a straight line like this. Okay, minus plus. So this value is WL by 4. This also WL by 4. So this is your bending moment diagram. Here also same way. So number of points of contraflexure is 1. So this is POI, point of inflection. Point of inflection is 1, point of contraflexure 1. This is complete behavior. They can ask you how the SFD BMD look like, or they can ask you what is the maximum shear force, maximum bending moment, or they can simply ask you what is the moment at A, or what is the delta, WLQ by 24 EI. Any one quantity they ask you, that is 2 minutes time. But you can complete that once you know the deflection profile and its values, maximum of 30 seconds, you can close the problem. Now, it is now one more example we will take. They asked a question like this. Moment at B is, this is a beam, okay, connected to a rigid block like this, and this rigid block is sliding. And on this one, he has kept a load W. This point, let us say AB. some length L, moment of inertia I say. Now we want to know what is the moment at B. This is a stiff block. So much story they write it, a stiff block. To that block we have connected a beam AB, and that block there are rollers and it can only move vertically down. This diagram we know how it will behave. Now what is the moment at B? Based on the description, first when load W is applied, it will go down. Then how the deflection profile is, that you plot correctly. Then that deflection profile will tell us what should be the moments. So this idealization, when it comes down, here slope will be maintained as it is. Line diagram we will show now. This entire thing we will fix it like this. Okay. This point is A, this point is B. Now you have applied a load W, then this will sink down. The deflection profile will go like this, or you can show, if you want, you can show completely like this, your choice. Like this also we can show, and there we have applied a load W. That load W I am showing it like this. This is VB. So for this profile, we know it is 12 EI delta by L cube. This value is W. Okay, this naturally sinks down by some delta. He is not asking that. He is not asking only MB. What is the moment at B? But what we can find is VB, we know W, 12 EI delta by L cube. From this, what we can find is delta, WL cube by 12 EI. Then what is the formula for MB? We know MB is equal to 6 EI delta by L square. For this profile, 6 EI delta by L square. Who will give to the beam? To this beam, this fellow will give a moment of 6 EI delta by L square. Otherwise, slope will not be 0. So 6 EI delta means WL cube by 12 EI, 6 EI delta by L square. So you will get WL by 2. So moment at B is WL by 2. To find moment at B, first this profile you draw. This profile will tell us what is VB, and that VB value they have to give us. This is the action. Because of this action, delta displacement produced. Then if you know the action, displacement if you want to find, this is the formula, WL cube by 12 EI. So one of the options will be WL by 2. So like ABCDs they give you, we have to write it as WL by 2. Next, this is the first concept. What is that first concept? Both ends are fixed. One of that fixed is because of anything, and that fixed support, maybe it is a guided roller or a column or a wall. If that wall sinks down or that column sinks down or that guided roller moves down by delta, any meaning is same. Okay, so this is what it comes. Supposing that one is hinge support, one end fixed, one end hinge support I gave 3A delta by L square. How questions come on that? Let us see. For the fixed beam shown in figure, if the support A yields and rotates by theta, moment at B is. So, this is the question. This is a fixed beam. There is a central hinge, a floating hinge, you can take it, A, B, C. This is a float, once put a circle means floating hinge. He has given this EI value as infinity and this is EI itself. That means AC member has infinite stiffness. Infinite stiffness means infinite moment of inertia will not be there. When compared with this beam BC, this may be 6 to 7 times stronger, say. That 6 to 7 times stronger, if this is I, this may be 7I. We idealize such a heavy beam as infinitely stiff beam. Okay. So, this support A, fixed support is supposed to be vertical. It will not permit the beam AC to rotate. Okay. Now, if the support A due to some reason yields and rotates, yielding means it is not sinking, yield simply means resigning, yields and rotates. That means it should not rotate, but it yielded and rotated. That means it resigned and rotated by theta. It yields and sinks by theta, delta, that way. Simply write sinks by delta also okay, but it yields and sinks by delta also meaning the same. There yielding means it resigns and moves down by delta. Supposed to be there, but it could not be there. It comes down. Suppose I am here, you push me. Suppose I am very strong, I will remain here only. If your push is so high, I have to resign. I yield and move down by delta. I yield and fall down. I resign and fall down. I resist. If I cannot, I have to resign and fall down, or I will translate. That is the meaning here. I yielded and rotated, yielded and fell down, whatever way it is. There the yielding means resigned and rotated by theta. We should not show translation and rotation. Okay. Next. Now see, based on the description, it is supposed to be vertical. Now it is not vertical, it rotated by theta. If support rotates by theta, AC member also will rotate by theta because 90-degree angle should be maintained. That is a rigid thing. Why support rotated? Beam does not know. Some reason, maybe this is the support was there, maybe in the soil or whatever problem was there, you didn't build the wall properly and it fell down. Soil, you didn't put sufficient good foundation. So, if I put it like that, based on the description, this length is L, this length is also L. First, we must draw the deflection profile. For any one question will come on MDM, either sinking of support or earlier concepts I gave, carryover moment, carryover factor. Okay. So, now if it's based on the description, first draw the deflection profile. Okay. This point A, C, B. Now, this rotated by theta means like this. This angle is theta. Then to maintain 90-degree line, naturally it will go down like this. This angle is also theta. Okay, like that. Next, because it is infinitely stiff, strength of materials you have studied that it will not bend. EA infinity means it will not bend, but it can rotate as a rigid body. Now, why it is rotating? Because support is rotating. Because support and this fellow connected. Suppose I am standing on the table. If the table is moving, because I am standing on that, I will also move with that. Why I am moving? Nobody applied any force on me. Because I am standing on the table, why is table is moving? I don't know. Someone might have pulled it. If it is moving, because I am standing there, I will go with him. Supposing that if I am statically indeterminate one, I will offer some resistance. I am statically determinate, say, then I will not offer any resistance, I will simply move as a rigid body with him. Okay, like that. Now, this is theta, this is straight line. Why straight line? Because EA is equal to infinity. Okay. Now, how this deflection profile, this way, why C went down, this fellow doesn't know. It went down, so naturally this will bend now like this. like this. See, on CB member there is no load, but C moved down. It is like a support, it is moving down. Why it is moving down? Not because of the load on this structure, because this fellow has some external connection and that fellow moved. This length from here to here, if this is L, this is theta. Theta will be generally, you have to assume that very small only. Arc length is L theta. So, delta is equal to L theta. Now, you see, in this case, this fellow might have pulled him down. With how much force, we don't know, but it moved by delta. Some force is there, we have to find out. We can find if we want also that. Okay, delta. For this profile to happen, if delta is known, strength of materials what happened? W is given, then moment we know, W into L. If load is not given, if displacement is there, then what is the moment? We know that formula also, MB. 3EI delta by L square. If load is given, we could have written W into L. If load is not there, displacement is there, 3I delta by L square. Now, what is delta? 3EI delta means L theta by L square. So, you will get 3EI theta by L. One of the option is this one, 3I theta by L, like that. Okay. Now, this profile, you see, it's a cantilever beam deflection profile. Once you know the cantilever profile means it is 3I delta by L square, fixed, that is all. Okay. Now, let us see a frame. This I remove. For the frame shown in figure, force P required to move the girder AB girder means beam, girder AB through a horizontal displacement. Through a horizontal displacement delta is, now this is the problem. Okay, this is the beam, this is the force P, this is A, B, let us say C, D. This length is L, I, length is L, I. This EI is infinity. They can use the wording EI is infinity or very stiff beam. Very stiff beam also implies EI is equal to infinity. Instead of giving EI infinity, they give very stiff beam, say. Then also you take EI infinity and manage the problem. Okay, implies EI is equal to infinity. Now you see, you push it. This is action. Otherwise, it will not move at all. He is asking now how much delta. So, due to this force P, you push it the beam right side. Then that deflection profile will tell how much force is required. See, it is like this. It's fixed. Okay. Now push it to the right side. It's fixed one. 90-degree angle should be maintained because this will not rotate, it will only translate. So, this is the deflection profile. This also will move by delta. Now, here slope is 0, then it will go like this. Okay, 90 degrees, 90 degrees. This A goes to A dash, B goes to B dash. You are applying external force P, applied force is P. This is the profile. For this profile to happen, all the values, first you draw deflection profile, then this we know, 6 EI delta by L square. This value is delta. This is also delta. And here moment is again 6 EI delta by L square. So, these are the moments exerted. This moment is exerted by the footing on the beam. This moment is exerted by on the column. 6 EI delta by L square is exerted by this stiff beam on this column. So, when I show this free body diagram, what this is doing on this one, what footing is doing on this one, we have to show. Now, here we know to make the slope 0, this is 3 EI delta by L square, 0. Now, the reactions also we know. Here how much it will develop? This value is 12 EI delta by L cube. Here right side 12 EI delta by L cube. Here also for this profile to happen, it should be pushed right side by an amount of 3 EI delta by L cube. Here left side it will develop like this 3 EI delta by L cube. Now, any one question, whatever they ask you, we can answer from this one. He is asking what is P. This one, if you remove it, first apply the delta displacement. For this displacement to happen, this much force you have to apply, and that is what we have done. For this column, this much displacement to happen, this much you have to apply. Now, both columns should move right side. So, this plus this amount 12 plus 3 15 EI delta by L cube amount of force if you apply, then this will move by delta. For this delta to happen, this also should happen. For this to happen, this much force is required. For this to happen, delta, this much force is required. Since you have to push both the columns, your P will be shared by these two columns like this. So, this is your action. This action is nothing but this plus this is action. This what I have given earlier. Action means you have to apply some force. This action is supplied by P. So, this is nothing but this one. So, P is equal to 12 EI delta by L cube plus 3 EI delta by L cube. So, you will get one of the options is this one, 15 EI delta by L cube. Okay. Supposing that if they ask you to find what is delta, you can find this one. Next question is displacement delta due to P is, how much is that? Now you see delta is equal to P is equal to 15 EI delta by L cube. So, you will get delta is equal to PL cube by 15 EI. So, this value delta is PL cube by 15 EI. Now, what is the reaction at A if they ask? Let us say. Reaction at A is horizontal reaction. So, what is the horizontal reaction HA? You will get 12 EI delta by L cube. That means 12 EI delta means PL cube by 15 EI. by L cube. So HA will get 12 by 15. That means 4, 3, 4, 3 5s. 4 by 5 means 0.8 P. L cube cancel out, P cancel, 12 by 15 means 3 fours, 4 by 5, 0.8 P. HA is 0. P. Naturally, if you want to find HD, say, HD, it has to be 0.2 P only. Then if you want to find moment at A, anything they can ask you, MA is 6EI delta by L square. So, you will get 6EI delta is PL cube by 15EI, 6EI delta by L square. So, you will get 6 by 15, 3, 2, 2 by 5.4 PL. So, like that. So, moment at A is 0.4 PL, HD is 0.2 P, like that. Any question they ask you, you should manage this way. Now, we have dealt with two members. You are applying P. P will be shared by the two columns. It is not necessary that always two columns or two members only should share. Same problem, if I turn it 90 degrees, I will get first problem. First problem what? Two beams, both are fixed, rigid block of weight W. Turn it 90 degrees. Now one end fixed, one end hinge, rigid block of weight P. See, say that identical nature you observe, that means analysis you observe, then no problem will threaten us because we know how to draw the deflection profile. Then that will tell you how the force P will be shared and how much delta is, how much reactions are developed, what is the reaction or what is the shear force. Anything in the same way we can calculate. This is two members, not necessarily two members. If four members are given, say, same way it will share. Now, one example will take when four beams support a load W. First problem when I gave was two beams are like this. From front view, one is at this level, one is at below level. Not necessarily one below the other, they can be in the same plane, but horizontally they can be there and you apply the load W. That way also your applied load will be shared by all the beams. Not necessarily one below the other, one besides the other also it can be there. Now see, for an octagonal hall of side A, four beams are provided for supporting a fiberglass roof. Why that fiberglass roof they give is fiberglass means almost weightless, we can take it. Okay, for supporting a fiberglass roof, the beams are fixed The beams are fixed in the wall at corners. And monolithically connected. At center C. A vertical load P is to be suspended at C. Determine the deflection at C. Deflection at C. Find maximum shear force and bending moment in the beams due to load P. So you have to find maximum shear force, bending moment and maximum deflection at C. Then the structure is like this. Orthogonally connected means, that means an octagonal hall is like this. Okay. Say it's like something this way it's going. Okay. An octagonal hall is this way. What we are showing is the top view. Beam 1 1, 2 2 beam is this one, 3 3, 4 4. This point let us say C. Of side A means this is A. Now, if you see our hall, it is a square hall. That means 4 sides are there and some roof is there. This is a square hall. You can have rectangular hall. You can also have octagonal hall, means 8 sides are there. Octagonal means like this. Maybe architectural point of view, instead of a square, they put one octagonal hall. At the top, to prevent from sunshine and raining, they put a 4 beams. They have attached 4 beams. On top of that, they put a fiberglass roof. Fiberglass roof means it is like transparent one, weightless, you can take it. 4 beams, when they are connected at the center, maybe they have attached one chandelier whose weight is say P. When you hang one load P, and due to that load P, all 4 beams deflect by the same amount. Why? Because they are monolithically connected. Once you hold the joints and pull it down, all beams will deflect by the same amount. Okay. So he is asking you how much the C point deflects. At the center, how much it deflects, and what is the shear force and bend moment in any beam. Now see, in the top view, when we see one, you can treat them as 8 beams or you can treat them as 4 beams, our choice. Okay, 4 beams means one full beam you can take it, then 1 2 3 4. 8 beams means I can take, this is one beam, 2 3 4 5 6 7 8, whatever way we want we can treat it. Both ways we'll try to analyze which idea, whatever idea you get in the exam, it takes only 1.5 minute time. But to get that idea, they have given us around 6 to 7 minutes time. It is actually a 20 marks question. in one of the civil services. But in GATE type exam, it can be given as a 2 marks question. You must complete in 1.5 minute time. Okay. So this is now the plan view they have given. This side A. Naturally, this angle is 45 degrees. Okay. This angle is 45 degrees. If you bisect it, say like this, this length is A by 2. This length will become A by 2. This angle will become 22.5 degrees. Let us call this as A, C, this is B. This length of the beam, this you take it as X and X. This is fixed here and here. ACB as a beam we can take it as a single beam. So two ways of analyzing this one. First method. So load P is shared by 4 beams. First problem when we talked one beam here, one beam below. Now all 4 beams are side by side. One is going like this, another going this way, another going this way, but all of them are in the same plane, not one below the other. But sharing is there. Okay, your load will be shared by all of them. So once they are sharing, when you can put below or side by side, both mean the same. So if I take this x value, if I want to find from this triangle, sine 22.5 is nothing but opposite side is a by 2, by adjacent by hypotenuse 90-degree angle is here. So sine theta is equal to opposite side by hypotenuse. So a by 2 by x. So x you will get a by 2 sine 22.5 degrees. So you will get 1.32a. X value will get 1.31a. Say whatever value. Now you see 1.31a. This is 1.31a. This is also 1.31a. That ACB beam alone you pluck it out and keep it here. This beam, this is one corner A. This is C. Center is C. This is B. Now at center when you are applying load P, there are 4 beams. They will share equally. So on AB beam alone, your load is P by 4 only, because AB was there, 2 beam, 3 beam, 4 beam is there. One beam share is only P by 4. This length is 1.31a. This is also 1.31a. So see the deflection profile. Both ends are fixed. Center we are hanging load. The deflection profile is like a both ends fixed beam. We know how to manage this type of profile. Okay. What is the fixed end moment? MA. The standard formula is WL by 8. MA is WL by 8. This P by 4 I can take W. This total length we can take it as L. If W is there, L is there, we know MA is PL by 8 and VA is W by 2. Same thing here also. MB is also WL by 8, VB is W by 2. Okay. Now, what's the maximum shear force? W by 2. What is W? P by 4 by 2. So, P by 8. Next, maximum bending moment. WL by 8. W means P by 4. Length is 2.62a. So, WL by 8. So, you will get 0.08 PA. Then maximum deflection. This is your Y max. YC. Maximum deflection at C is nothing but YC. We know that formula also, WL cube by 192 EI. WL cube by 48 EI for a simply supported beam. Once you fix them, deflection reduces by 4 times. So that means WL cube by 48 into 4. So WL cube by 192 EI. So much less deflection. So W means P by 4. Length means 2.62 A. WL cube by 192 EI. So this value you will get 0.023 PA cube by EI. 0.023. Like if is now the problem finally boils down to like a fixed beam deflections. Once you idealize that it behaves like each beam behaves like a fixed beam subjected to central point load, find standard formulas. This alone is a 20 marks question. But to get this idea from this diagram to this diagram, you can spend 5 minutes time. That was once civil services. But now our gate problems, similar problems are given for 2 marks only. Okay. So like this is deflection YC. Supposing that you didn't get this idea, you got only that 8 beams are there, 8 beams are kept radially and it's getting pulled down. That means only AC beam as a single beam you take, say, then like this 8 beams are there surrounding that. Then such cases each beam will take P by 8. Out of P by 4 this will take P by 8, this will take P by 8. So that way also we can take it. So this profile also we know how to manage. Suppose this a fixed beam profile, if you take subjected to central point load, only half beam you take, say, cut, pluck it out, keep it side. This profile where slope is 0 but sinks by delta some value, we know how to manage that profile. Once you know the reflection profile exactly how it looks like, then all the fixed beam subjected to sinking of support is there. All such formulas you can attach. That you see in the second method. In the second method, we will write P is shared by 8 beams, let us say. This idea you have got it. Then AC beam alone we will take it. A, this is center point. This distance is only 1.31 A. And C sinks down by delta like this. This is YC. Maybe some delta. Then what is the value here? P by 8, because P is shared by 8 beams. So P by 8 is nothing but 12 EI delta by L cube. L means 1.31 A cube. 12 EI delta by L cube. So VA is also same. P by 8. Then MA. WL by 8 we cannot write for this profile. For this profile, 6 EI delta by L square is the formula. So from this you can calculate delta. P by 8 into 1.31 A WL cube by 12 EI. So you will get 0.023 PA cube by EI. Same formula. Delta is nothing but YC. Then maximum shear force is equal to VA, nothing but P by 8. Then maximum bending moment, MA. This is nothing but 6 EI delta by L square. So 6 EI delta means 0.023 PA cube by EI. 6 EI delta by L square means how much formula? 1.31 A whole square. So this you will get 0.08 P into A. So P by 8, 0.08 PA, 0.023 PAQ by EI. See here we have taken AC deflection profile. Like this it looks. Only this much. Full profile you take, another half you take it. It's like a fixed beam subjected to central point load. Both profiles are identical. Next. So now next question we'll take it. Frame problems. Frame analysis if we have to make it. Now see here next question. Ratio of fixed end moments. See they are asked question itself fixed end moments due to sway, that is MSBA by MSCD is. This is A, B, C, D. Length of the column is Li, this is L by 2, but this is 2I, let us say. BC not given, though we don't require also. Ratio of fixed end moments due to sway means this frame can sway to the left, can sway to the right, depending on whether horizontal load is applied to the right or to the left. If load is applied to the right, it will sway to the right, otherwise it will sway to the left. Then what will happen if it all frames sway? Two types of analysis we have to do. Due to the applied loads, first you calculate all the final end moments, considering that the frame doesn't sway. Frames sway to the left or right at the beam level because of the unbalanced horizontal forces. If no unbalanced horizontal force is there, why should it unnecessarily sway? It will remain vertical position only, initial position only, and it will be in equilibrium. But if there is any unbalanced force is there, due to that force it will sway. Once it sways, the resisting moments will develop. Till the resisting force becomes equal to your applied force, it sways and stops. Because resistance developed in the deflected shape, sway moments will develop. And earlier we have seen if it sways to the right side, the reactions, fixed end moments, all reactions will develop and keep it in equilibrium. Just because you apply force P hundreds of kilometers, it will not frame will not move. After it sways by delta, it stops. Okay. Now, how much is that sway? Delta, if I know, we can manage the problem. Suppose if we don't know, we have to take two analyses. One is due to applied loads, assuming that the frame doesn't sway. What are the moments developed? And from that, you find what is unbalanced force you will calculate. That is called non-sway analysis. Assuming that the frame doesn't sway, non-sway analysis we have to do. Now you will find at the beam level what is the unbalanced horizontal force. Because of that force it will sway and joints also rotate. First, then sway analysis we have to do. Assuming that all the joints are fixed, like in MDM, find the fixed end moments due to sway. After finding the fixed end moments due to sway, then release the fixity. Then unlock the joints, then find the sway moments, final sway moments. Then because loads are there, frame is swaying, you apply principle of superposition. Non-sway analysis, final end moments you will get, add them from the principle of superposition to get the net final end moments. So in the final deflected shape position, after rotating the joints after swaying, then it will be in equilibrium, final end moments we will get. So that is the process. That entire process, even if you take 3 members also, it will take minimum 45 minutes time. If the loads are simple, maybe say 20 minutes time you can complete. Because you have to do non-sway analysis, find the unbalanced sway force. Then sway analysis, then again add the moments. So sway and non-sway analysis problems in the exam, complete analysis, they cannot ask. They can ask only this much. If you fix here and if it sways, what is the fixed end ratio of the fixed end moments? Because that is a small part of our problem. So first you assume that it is pushed to the right side. Don't want, push it to the left side, our choice. So assuming that the column is fixed at, because at A already fixed is there. Okay, this is A, B. Assume that it sways to the right side like this. If this is delta, let us say, this is called sway. Okay, now assuming that all joints are locked, this is the deflection profile. This we change. Okay, this B will go to B dash. Next BC beam, this BC, fix them. Okay, B, C. Now it sways. As a rigid body, it will sway because B went to B dash. Then C will go to C dash like this. And this is delta. This is also delta. So straight configuration remains straight only. So no fixed end moments will develop in BC member. BC member fixed end moments will develop due to sway only when there is a differential settlement. So when I push it to the right side, AB column deflection profile is like this. Lock all the joints, push it. Then BC member, lock the joints, push it. No fixed end moments will develop. Then CD member. Now see, D is already hinged one. So keep that D hinge as it is. Okay, fix this one. C, D. C has come to C dash. That means here also C will go to C dash. Somewhere here. Now this deflection profile is like this. This length is L by 2, 2I. This has to be delta only. Because this is delta means this is also delta. So this is the deflection profile. He is asking this moment we call it as MSAB. Fixed end moment due to sway at A for the member AB. Anticlockwise, so you can take it as minus 6CI delta by L square. Here also same thing. Minus, this we read it as fixed end moment due to sway at B for the member BA. Minus 6EI delta by L square. Now due to sway, how much is that? Due to sway at B for the member BC is 0. Here fixed end moment due to sway at C for the member CB is also 0. If at all any support sinks by delta, that means D or A sinks by delta, then deflection profile will come, fixed end moments will be there. No support settlement, so only swaying, so these two will be 0. Now here anticlockwise movement like this. This is, we take it as fixed end moment due to sway at C for the member CD. When far end is hinged, we know anti-clockwise minus, this is delta is same, minus 3e, I means 2i, delta is same, L means L by 2 square. Okay, like that. He is asking this ratio, MSBA by MSCD. MSBA by MSCD. This is minus 6EI delta by L square, by that you can write minus 6EI delta by L square into, so this MSCD I can write it as minus 6EI delta by L square. This becomes 4, right, into 4. So finally you will get 1 by 4. So one of the options is 1 by 4. That means MSBA, MSCD cannot be independent. If MSBA, let us say minus 6A delta by L square, let us say 10, some arbitrarily fixed moment. If this is minus 10, it has to be minus 40. It has no choice because delta is same. You fixed them. Now this is called sway analysis. First fix all the joints, push them by delta. Column, beam, column, they move by delta. Then the deflection profiles will tell us which column or which beam they developed fixed end moments. This is symbolic representation of fixing all the joints. So now the beam can sink, columns can sway. Fix them, sway them. Or beam means fix them, sink them. If sink is there. Sink is not there, fixed end moment is 0. Clear? Now, like this, first you lock all of them. But BC joints are not locked joints. So fix, then unlock it. Then your 6A delta by L square gets distributed. Here also it gets distributed. That means distribute here. Again carry over moment, distribute. Carry over moment, distribute. That means it will take minimum of say 6 to 7 minutes time to do only sway analysis. So in the exam, like this 3 members also they will not ask us. Because 6 minutes, let us say you are doing fast, 5 minutes time is there. That much you can't get, 2 minutes time only you have to do. So sway analysis problems, if they give in the exam, 3 members they cannot ask. 3 members if they give, they will only ask you the ratio. Because only that you can find in 1 minute time. If only 2 members are there, then they can ask you to find the sway moment or the what is the reaction, etc. Like that. Okay, where you can complete in 1 minute or 1.5 minute time. If sway problem is given, they have to give us only 2 members. If 3 members are given, means they ask you what is the ratio of the fixed end moment due to sway. Process is this: fix them, first fix them, find the fixed end moments. Then find some ratio will get, some arbitrarily assume some sway moment. If this is minus 10, minus 40, distribute that. Then what is the sway force required for that much displacement you will get? Okay, for these movements how much force is required we will know. Then for actual force, sway force some 20 kilonewton, 30 kilonewton you get, say for that much what is the sway moment, linear interpolation you will do it, but in the exam numericals not possible. I'm giving you only the process. So you take a correction factor and get the corrected sway moments. So non-sway moments, corrected sway moments, add them, you will get final sway moment, final end moments. That's the process. In that, this is one example. Entire process, when you come for mains for 20 marks questions, we will discuss those long questions where only 3 members will be there, on pure sway problems they can ask in the exam. Okay, so this is the sway. Now let us see, we will remove one member, only 2 members are there. If the frames sway, then how the questions can be asked, how the moment distribution should be done. If only 2 members are there, fix it, unlock it. It gets distributed to only 2 members, that's all. So within 30 seconds you can complete the problem. If third member is there, carryover moment will come, again you have to fix it, then release, again distribute, and half will come here, again distribute, then that process takes 5 minutes time. So one is such example where only 2 members are there, we will see now. This is the question. A rigid jointed plane frame ABC shown in figure is subjected to a load P at joint B. Axial deformations in the frame are neglected. Even the statement whether they give it or not, we have to neglect only. In the MDM, we neglect them. In the frame are neglected. If the support C undergoes a settlement of delta is equal to PL cube by beta into EI. Beta into EI, comma. What is the value of beta? So that vertical reaction at support C will become 0. Now you see, as I told you, only 2 members must be given like this. It's fixed here. This point, let us say A, B, C. This length is Li. And a load P is applied here. This is our frame. Now you see, as per the description, support C settles by delta. Earlier problem, due to sway, what are the fixed end moments? Ratio of fixed end moments due to sway. So what you have done, you pushed it, you swayed the frame and found the fixed end moments. Now the question is not sway, it sinks. Support C sinks down by delta. If it sinks by delta, first fix them, sink it, then release the locks, because you are unnecessarily locking them. Why it sinks down here is, maybe if at all the support is sufficiently strong, due to P, what will happen? In this case, ABC only 2 members frame. If it is very strong, as in strength of materials you have studied, P will be taken by BC only. So vertical reaction at C becomes P. That's all. AB simply keeps quiet. No sinking, no movement, nothing, because load you applied only at the support like a joint. So if C doesn't sink, force in the member BC, axial force in the member BC is P compression. AB member, no shear force, no bending moment, no axial force. That we know from SM. Now he says C sinks down by delta, by PL cube by beta into EI. So much it sank down that vertical reaction became 0. If vertical reaction becomes 0, then what is the value of beta? Whatever may be that problem, first fix here, fix here, fix there, then sink it. How the fixed end moments will develop. Then distribute the fixed end moments. Then you will know the sway moments due to that sinking delta. From that free body diagram, you will know what that free body diagram will tell you what should be the delta so that reaction at C becomes 0. So it is like that. So your first step is, in this one, fixed end moments due to sinking alone. because no loads, applied load on the spans are not there. So no sway analysis, only no non-sway analysis, only sway analysis. Due to sinking alone, you have to find the moments. Fix first step. Fixed end moments. Due to sinking alone. Because due to applied loads, no fixed end moments. If applied loads are there, due to applied loads, you have to find what are the fixed end moments. Due to sinking, what are the fixed end moments. And from the principle of superposition, add net fixed end moments. But 2 times you have to add means another 20 seconds extra time waste. So they will not give applied loads on the span and also sinking. It's only time problem. So due to sinking alone, see here. First, fix it. Sink it. A, B. Like this it sinks. This value, let us say delta. This sway moment, fixed end moment due to sway at A for the member AB minus 6 EI delta by L square. And here fixed end moment due to sway at B for the member BA minus 6 EI delta by L square. Next B went to B dash. Now this BC member BC, this is second member BC. Now hold it, sink it. Once you sink it, B will go to B dash. This is delta. C will go to C dash. This is also delta. Then what is the fixed end moment? Fixed end moment due to sway at B for the member BC 0 because vertically it went down. If it's this one sways, then there will be some fixed end moment. But you see the deflection profile will tell you what are the fixed end moments also. MSBC 0 here. Whether you put clockwise or anti-clockwise doesn't matter because it is 0. And here also fixed end moment due to sway at C for the member CB 0. Next, distribution factors. Now see, at A we know wall member 1 0, at B BA BCC 0.5 0.5, for BA and BC 0.5 0.5. Next, end moment distribution. Which end moment distribution? Fixed end moment distribution. Fixed end moment distribution due to what? Due to sinking alone. Due to applied loads, we have solved so many problems how to distribute the end moments. Now, due to sinking, how to distribute the end moments. That you will take third step. End moment distribution. Okay, EMD enough to write. Joint joint A B C. Now distribution factors, by inspection you can find 0, 0.5, 0.5. Here it is 0. Then fixed end moments. These fixed end moments can be caused because of the applied loads we know have solved. Now these fixed end moments due to sway or due to sinking alone. So this is here minus 6 EI delta by L square. This is also minus 6 EI delta by L square 0 0. These are the moments required to lock them, but B is not fixed. In all earlier problems, one member is infinitely stiff, so joint didn't rotate at all. In the same position only, it is in equilibrium, simply swayed and stopped. Now He didn't give us that BC member is infinitely stiff. EI value only he gave. So at B, once it sinks, this is not the deflection profile after it sinks. So it joints rotate. So now you fix it. To fix joint B, you require minus 6A delta by L square. If it behaves like already fixed supports, no distribution, nothing. Same as this, will keep it. Now it gets distributed. To fix it, minus 6A delta by L square. Now to release it, you have to apply plus 6A delta by L square. That is called balance. So plus 6A delta by L square, how much? This 6 will be there as it is. You will get plus half of that 3A delta by L square here also, plus 3A delta by L square. Now carry over moment. This moment we went and applied 3, half of that is carried over here. So 1.5 EI delta by L square, and here this is also plus 1.5 EI delta by L square. Carry over moments. Now that's all. Problem is over. Now you can get final end moments. If BC member is infinitely stiff, there is 6 EI delta by L square. If at all is infinitely stiff, what are the distribution factors? 0, 1. So minus 6 EI delta by L square. Here 0 becomes, it becomes 6 EI delta by L square. Then 6 will be carried as it is 6 EI delta by L square. No half it is. It is same moment will be carried over as it is. That specific cases, if at all BC is infinitely stiff, how the distribution factors change, we will solve separate problem, all possible cases. Now you will get final end moments. You will get minus 4.5 EI delta by L square here, minus 3A delta by L square, this is plus 3A delta by L square, this is 1.5 EI delta by L square. These are the final end moments. Now you draw free body diagram. That free body diagram will tell you how much should be the delta. See, in terms of delta, that free body diagram will tell you how much should be the delta, so that VC will be 0. See, draw free body diagrams. This is AB member. This is fourth step, support reactions. This is our standard stepwise procedure, support reactions. This is one AB member, BC member. Okay, A, B, B, C. If load is applied at the joint B alone, then it will be shared by the two members. You should not show that free body diagram P completely here or here. Like strength of materials, if load is applied at the joint only, that will be shared. So your P should be kept somewhere in air like this. Because part of P is taken by AB, part of P is taken by BC. So P we should not keep on any free body diagram. Then how much of P is taken by AB? This free body diagram will decide how much of P will be taken by AB. Okay. It should not be kept on any free body diagram. Why? Because P is shared by two members. Okay. Now in this length is L, this length is L. Now end moments you will show. Here minus 4.5 means anti-clockwise. 4.5 EI delta by L square. This is minus 3 EI delta by L square. Because minus only put anti-clockwise. This is plus, that means clockwise. 3 EI delta by L square. Half of the moment is carried over 1.5 EI delta by L square. If it is infinitely stiff, same moment is carried over to keep it in equilibrium. Okay, that case we'll see in the next free body diagram. Now we see reactions. 4.5, 3, both anti-clockwise. To balance it, clockwise should be there. How much? M by L, 7.5 EI delta by L cube. M means 4.5 plus 3, 7.5. Because both of them are acting anti-clockwise, to balance it clockwise. So reaction is M by L, 7.5 EI delta by L square by L means 7.5 EI delta by L cube. Here also same, 7.5 EI delta by L cube. Then on this free body, there will develop horizontal reaction. See, both clockwise. To balance it, anti-clockwise. That's all will develop. 3 plus 1, 4.5. So you will get 4.5 EI delta by L cube. Here also 4.5 EI delta by L cube. Now you see this free body diagram, vertical reaction should be 0. That means 7.5 down. Then how much should be here? If at all there is a reaction, say. Out of P, this fellow has taken 7.5 EI delta by L cube. Then what is remaining? P minus 7.5. So the remaining force here is, this is out of P, this fellow took 7.5. Remaining force here is downward only, it should be P minus 7.5 EI delta by L cube. This much force is there here. And if this is down, to balance it, this is P minus 7.5 EI delta by L cube. Now you see, add these two forces, 7.5 plus P minus 7.5. Net force is P when you club them. So that force P is equal to that. Once you add these two forces, I should get this. Now cut, throw that out. Sum is should be P and P tallied. This is the free body diagrams of two members. Now he says this compressive force he wants it to be 0. It sinks so much amount that P minus 7.5 EI delta by L cube value is 0. Vc is 0. So he says that Vc is equal to P minus 7.5 EI delta by L cube is equal to 0. Why 0 given? Then what is delta from this one? P is equal to 7.5 EI delta by L cube. So delta you will get P L cube by 7.5 EI. So all beta is equal to 7.5. So one of the options is 7.5. 4 options were given. So it will be 7.5. 7.53 like that they have given. So this is a stepwise procedure, but in the exam I think this must be there. This you don't have to show. Second step you can skip it. First find fixed end moments, draw end moment distribution, draw free body diagram. That free body diagram will tell you how to get that P minus 7.5 is actual reaction, but that reaction we want it to be 0. If not 0, we could have simply stopped P minus 7.5. One frame problem we have drawn in the EM end moment distribution, frame beam problems. Reactions also we have shown. What is the axial force in AB like that? You got 1.5 M by L like that tension, 1.5 M by L compression. If that value you want it to be 0, say, then what could be M? Like that question. Okay. Now, if you draw the final end moments, if you show, the deflection profile will look something like this. Now you see, if you show the free body diagram, third step, fourth step, this is extra. Deflection profile. This is A, B, C. Now B has come to B dash somewhere here. C will come to C dash. This value now delta. This is also delta. BB dash. Now it rotated. If you show this free body diagram here, the moments, this is A, B. Already we have shown, but that we can take it B, C. This is anti-clockwise 4.5. So A delta L square common, let us say this is 3, clockwise 3, this is 1.5. This stand here. Now if you stand here, look at this one, it will hog, but this is sagging. Fully if you write it 3EI delta by L square. Okay. So this is sagging, this is hogging. So here it should sag, it should hog. So there must be one point of inflection somewhere. Okay. Right. Now it should sag means sag profile should be drawn. It should hog somewhere here. In between somewhere point of inflection may be there, but it will rotate like this. If you drop a tangent, there is some theta b. This is theta b. Next, come to this member. Stand here, look at this one. This is sagging, this is hogging. Here also you must show that it is sagging. This is theta b. Here also it will rotate so that 90-degree angle will be maintained. And this is hogging. It should hog means this profile will be like this. Hogging like this. Somewhere here you will get point of inflection. Here somewhere one point of inflection. This is sagging, hogging. It should sag. This should hog. Okay. So 90-degree angle should be maintained. So if you drop a tangent here, this total angle now becomes 90 degrees. This also will be theta b. This is 90 degrees. Okay. This b rotated by theta b. This may also rotates by theta b. This is a profile. See here, this free deflection profile tells you that if the reaction, vertical reaction at C0, let us say, if vertical reaction at C0, this out of P load it is not taking, but moment it will take. See that free body diagram tells you that reaction is 0, but moment it will take. So it will not bend like a cantilever. Reaction here is 0, your P, entire P is taken by this only, but it won't bend like a cantilever because B is a rigid joint. So if you draw cantilever deflection profile, then delta will become PL cube by 3EI. Then beta is 3, it will get, first option beta is 3. Then if you take cantilever profile, gone. If your deflection profiles go wrong, solutions will never be correct. Okay, so this is how the deflection profile it goes. This will tell you that though vertical reaction C is 0, does not mean that BC will take 0 moment also. It will not remain vertical, it will bend because of the rigid joint nature. So that's why this profile is also not like a cantilever. So deflection delta PL cube by 3A we should not write. Free body, you have to distribute the fixed end moment, then draw free body diagram. That will tell you what is the value of beta. Okay. Supposing that only 5 minutes. Supposing that if you take the EI value becomes say infinity, I think this is over. I will tell you how much, what are the changes that we may get. Same problem I am showing. A, B, C. This is P. This EI value is infinity. This is simply EI. L, L. If VC is equal to 0, beta how much? Okay. Now, fixed end moments when you take it, as in the earlier problem, assume that B sinks by delta. B's value of same problem I am giving. So, fixed end moments. It will not change. This is M sway at A for the span AB minus 6 EI delta by L square. Here MSBA minus 6 EI delta by L square. B has come to B dash. Then BC member if you take it, EI is infinity, BC. B has come to B dash, C will come to C dash. Okay, now fixed end moments are 0. MSBC, MSCB, both of them are 0 because straight line only it will become. So distribution factors. Now see, after this is done, distribution factors are what? At A, 1, 0, here is how much? This is 0, 1. Distribution factors for BA and BC are BA is 0, BC is 1. So then third step is EMD. In the end moment distribution, here you see distribution factors, the same problem we can make use. If at all BC member infinitely stiff, this is distribution factor 0, this becomes distribution factor 1. Okay. Now fixed end moments same. Balance, how much it will become here? This will remove. This is the next problem we are talking. So 0 means 6A delta plus 6A delta by L square is the moment you have to apply. 6, this will take 0 moment. This will take same, full it will take 6A delta by L square. Okay. Now carry over moment here, already it is 0. From here 0 carry over moment. Out of 6, how much is carried over? If infinitely stiff means same moment is carried over. Half moment is carried over only if you have the EI value. That means this is A is infinity. So same moment is, it's like a now cantilever beam. So 6EI delta by L square is carried over. Same moment. So final end moments now will become like this. One such problem I have given you for this one. So this is minus 6EI delta by L square. This is also minus 6ei delta by L square plus 6ei delta by L square. This is also plus 6ei delta by L square. So carry over moment, the carry over factor becomes 1, like for the cantilevers. Okay. So now for this profile, now minus the support reactions when you are writing. This also I will remove. Here anti-clockwise 6ei delta by L square. This is also 6ei delta by L square. Anti-clockwise, so clockwise this will become 12ei delta by L cube. This becomes also 12ei delta by L cube. Now this will become P minus 12 ei delta by L cube. This is also 12. So these moments also we can change. This anti-clockwise 6ei delta by L square. This is also 6ei delta by L square. Okay, so like that the forces will develop. Now in this case, since clockwise or there anti-clockwise, some reactions will develop and it will be in equilibrium. That points we are not interested in that. Okay, we can show that reactions also to make it completely in equilibrium. Okay, now so what is the delta now? Say Vc is equal to 0. That means P minus 12 ei delta by L cube is equal to 0. So P will become 12 ei delta by L cube. So delta you will get PL cube by 12 ei. So beta will become 12. That means if BC member is infinitely stiff, beta becomes 12. If simply I value are given, beta becomes 7.5, like that. Okay. If EI becomes 0, then moment also it will not take. In this case, if EI is 0 means that it is a weak beam, then it behaves like a cantilever only. This member will simply vertically go down. So that is next example we can take as a note. This I think these are the changes we have to make if EI is infinity. If EI is equal to 0, see here, now I remove this part. Next, if EI is equal to 0 for BC member, then beta how much? This is the frame. EI is equal to 0. It implies that it is a weak member. It means that it cannot take any bending moment. This point A, B, C. You are applying load P, L, L. Now, because it cannot take bending moment, it cannot take reaction, it is going down. So, deflection profile is simply like this. Freely it will bend. That's all. No 90-degree angle, because weak beam means 90-degree angle will not be maintained. So, delta will become now PL cube by 3EI. So, beta will become 3. For this case, this is the deflection profile. This will simply go down, that's all. C will come to C dash. This is also is going down set by delta. So, this point you have to remember, this is the deflection profile. Here, why we didn't maintain 90-degree angle? Weak beams, that means weak column or weak beam, if EI is 0, it means that it cannot take any bending moment. It will take only axial forces. So that axial force also it is not taking. That means it is simply useless. So 90-degree angle also will not be maintained if EI is equal to 0. It's like a cable you attach it to this member. That's all. So reaction is 0, moment is 0. So simply vertical it will go down. No 90-degree angle maintained. Entire piece taken by this column and this beam AB. In this no bending moment, no reaction. Such cases only beta becomes 3. But in the given question EI is equal to 0, he didn't give. EI only is there. That means beta becomes now 7.5. So beta can be 7.5, it can be 3, it can be 12, depending on whether this is EI as it is, EI is infinity or EI is 0. This is a complete information about the structural behavior. Some more such deflection profiles we will draw when we are dealing with the cable structures also. That means there I will define EI is equal to 0 means what, infinity means what. Again we repeat these problems there.